Okay, so I want to talk about a bouncing collision. Let's say two billiard balls. Two billiard balls pool balls on a pool table. They are relatively bouncy, relatively elastic. So they may not be completely elastic, so we don't need to assume that. But at the end, I'll say, what if it was completely elastic? What could we do? But let's say that we hit a little bit off center. So let's say that you got a cue ball and we're trying to hit the 8 ball, and we're a little bit off center. Now, give them different masses. Maybe they have the same mass. Some pool tables, the cue ball is a little smaller than the rest of the balls. Doesn't really matter. Just for the most general problem that we can solve, let's just keep them different masses. And let's say that we shoot one at the other, and after the collision, right, M2 goes in this direction, and M1 goes in this direction. And we want to compare their directions compared to the original. And so now we got a few more variables here. We can deal with it, but we got a few more variables, right? We've got that M1 was going upwards and M2 was going downwards. And let's call we'll call this theta 2 and this theta 1, right? They've got two different angles that they're going at. So that's a pretty typical pool table hit. We can solve this problem entirely without numbers just to see how it's solved. But in order to give you some numbers to play with, let's say that in this case, M1 does indeed equal M2. And let's say we're just tracking M1. And so V1 initial, right, the initial velocity of ball 1 is, I'm looking at my notes, 3 meters per second in the x direction. In the plus x direction, I just put the x, the plus sign in a different place. And the final velocity of ball 1, V1 final. Yeah, so V1 final has a magnitude of 2 meters per second, is 30 degrees up from the plus x direction. And so the question is what is the velocity of ball 2? What is V2 final? In other words, what's its speed and angle? Okay, just put those in the picture just to make sure you understand. Okay, so how do we solve this problem? Well, it's a collision. So the only thing we know, because we know it's not necessarily completely elastic, energy is not necessarily conserved, we know, though, momentum is conserved. So how do we deal with that? Momentum is conserved. Well, ta-da, right? It's momentum conservation. Momentum initial equals momentum final. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Momentum conservation. Sum up the momentums before and after the collision. So now this is a two-dimensional problem, right? It's a two-dimensional problem. Look back. We got to take into account 2 dimensions. Let's go ahead and draw our axes. It's a two-dimensional problem, so we got to choose a coordinate axis. Let's make plus x to the right and plus y up on the page. And then just break it into 2 dimensions. So this is something you have to be able to do. Break it into 2 dimensions. Just deal with things in the x direction and then just deal with things in the y direction. So we need to be able to take components of the vectors in the x and y direction, conserve momentum in the x direction, conserve momentum in the y direction. Let me show what that looks like as equations and then come back here and take the components. And an equation, right, all that means is in the x direction, we go back to the right color, in the x direction we've got M1 V1 initial in the x direction plus M2 V2 initial in the x direction. So I went ahead and wrote it all out. Excuse me, let me cough for a second. So I went ahead and wrote it all out, right? We just separate it into x components and y components. Take the components, and so we just have 2 equations where we had 1. That's all, right? Broke it up into x and y direction. By the way, we could have done this with the last problem with the 2 cars that were colliding, coming at right angles. It was just as easy not to, but we could have broken it into the x direction, y direction separately and found the components separately that way. So we have to be able to break things into components and see that where we had 1 equation, we now have 2. And that's always the case. When we have a 2-dimensional problem, we have whatever number of equations we have in the x direction, we have the same number of equations in the y direction. And now this is where I don't want to take the time. You need to be able to take components, right? So the V1 initial is all in the x direction. Let's go ahead and draw the components in. in red, right? This is all in the x direction, but V1 final has an x component and a y component, and V2 final has an x component and a y component. You need to be able to take those components. This is a basic part of physics. You've got to take a problem in 2 dimensions and take components in the x and y direction. So that's an exercise for you. Take the components. I'll give you a second, and then I'll write out the result. You don't really need a second because you can hit pause. Okay, taking the components from the previous page, we get what's below the red line, right? The first ball before the collision is moving in the x direction, so there's no component to take. The second ball isn't moving at all, so that's the first ball moving in the x direction, second ball isn't moving. This is the x component of the first ball after the collision. This is the x component of the second ball after the collision. And they're both moving in the plus x direction, so there's positive signs in front of both of those. In the y direction, neither ball is moving in the y direction before the collision. After the collision, the first ball is moving in the positive y direction. There is an implied positive sign. We could put the positive signs in front. And the second ball is moving in the minus y direction, and that's its component. So these are the 2 equations that we get for this particular collision. And so now it's simply, I don't know if it's quite so simple, but simply a plug-in. So now we're just going to solve for the final velocity or the final speed, v2f, and angle, theta2, that it makes with the horizontal. So we're just going to solve these 2 equations for that. So it's 2 equations, 2 unknowns. Everything else is known. It's maybe not trivial algebra. It's algebra, 2 equations, 2 unknowns. I'm going to leave the algebra to you. If you want to practice your algebra, do it. I'll tell you the answer. Pause, pause, pause. Here comes the answer. Remember that m1 is equal to m2. We didn't do that. If we just make m1 equal to m2 here, all the m's cancel. So then we're only dealing with velocities, speeds, and angles. But anyway, m1 equals m2. Plug in the velocity v1f and v1i, and solve for v2f and theta2, and you get v2f is 1.62 meters per second. Theta2 is 38 degrees. We already drew it. It's below the plus x direction. Okay, so the last thing is this an elastic collision? I don't know. I think I said I don't think it is, but is it an elastic collision? What does it mean to be an elastic collision? If it's an elastic collision, that means energy is conserved. Now, it's not on a slope, it's not going up or down, so by energy being conserved, we mean KE initial equals KE final of the system. So that means that the 1/2 m1 v1 squared plus 1/2 m2 v2 initial squared. Well, if it's an elastic collision, the question is are those kinetic energies equal? Okay, so if it's elastic, it means those 2 energies are equal to each other. So we can just do a plug-in. Since the masses are the same, m1 is equal to m2, they all cancel out, and it's a pretty easy plug-in. Okay, so plugging in, you can see by plugging in that the kinetic energy before is not equal to the kinetic energy after, so some energy was lost. We could even figure out how much energy is lost. How much energy is lost? Look at the equation. Oh, well, actually, I would have to know the mass. Sorry, I'd have to know the mass to know how much energy was lost. If, let's say, the mass was 1. If the mass was 1, then the energy loss is 4.5 minus 3.3. So it's 1.2. If the mass was 1 kilogram, it would be 1.2 joules of energy lost. But anyway, kinetic energy is not conserved. It's not an elastic collision. What if it was an elastic collision? If it was an elastic collision, then this statement here would be true, that the kinetic energy before would equal the kinetic energy after, if it's an elastic collision. And then we could use that as additional information. Let's say there was something else we didn't know. I gave you enough information to solve the problem and to get the answer you were looking for, but I could have given you less information and made it an elastic collision. With an elastic collision, we have yet another equation to work with, which is the kinetic energy conservation equation. But that's only if it's elastic. This equation is true, and it's more information. It's another equation. We could use that to solve. I do want to note that when we talk about elastic collisions and energy being conserved, because again, if we're assuming that momentum is conserved, we're assuming that the collision happens over a very short time, so we don't have to worry about external forces like gravity. And so that means that the potential energy due to gravity isn't at play here. So when we say that energy is conserved in an elastic collision, what we really mean is kinetic energy is conserved in an elastic collision. The kinetic energy doesn't change, but because the potential energy doesn't change either, because by definition we say it happens on a short enough time scale that we don't have to worry about changes in potential energy. We can certainly practice momentum problems over and over again, but they're all the exact same equations. It's all the momentum conservation in one dimension, x direction, or two dimension, x and y direction. That's just momentum conservation, period. We could do it with three objects. We don't usually. And then if it's elastic, we've got the kinetic energy conservation equation. That's it. That's all we need to know. But we do need to know how to deal with vectors, taking components, and that's pretty much it.